All right, this is the lecture on Chapter 4 here in our metallurgy class. So we're going to begin with the basic structure of metals. And talk about this. Now here are, of course, the learning objectives to be able to name metals in each of the three major metal crystal structures. So we have what we refer to as face-centered cubic, body-centered cubic, and hexagonal close packed. So we'll talk about more about what those are here a little bit later. We're going to understand how these metals can deform at the atomic level, while minerals and ceramic materials cannot deform without fracturing. So we're going to define the atom, the element, and the compound. We're going to recognize the relative size of atoms, compounds, and crystal grains. We're going to state four properties that distinguish metals from nonmetals. We're going to distinguish between the three major crystal structures found in metals. Again, going back to that face-centered cubic, body-centered cubic, and hexagonal close packed. So we're going to recognize there's a conversion of metal ore to metal and the oxidation of metal to form metal oxides, that these are chemical reactions but in opposite directions. So we're going to distinguish between a solution and a mixture as applied to liquids and solid metals. We're going to understand and identify grains in the structure of a metal alloy and understand how the term phase describes solutions in metals. So first off, when we are talking about our measurement scales, so some of you are already aware of some of the measuring tools that we use in the industry. So we are talking right now about metals defined by macroscopic properties. So, and these properties are observed and measured at eye. By the eye, so the standard unit of measurement here is in meters or in millimeters. So, but the atoms that we're talking about are much, much smaller and are measured in smaller units, so what we call a micrometer or a nanometer. So, notice the symbol, so between the two as far as micrometer, so, and a nanometer. So, and as we go, be aware, so when we're talking about a micrometer, the micrometer is a measuring tool that is used for precise measurements to within 1/1000th of an inch, or we can also use that to measure millimeters to the micron. So, but that again is a little bit different. So here we have a micrometer. So a difference between a micrometer and a micrometer or a micron, and the unit of measurement is 1/1,000,000th of a meter, and of course the symbol here is a micrometer. So understand some of the differences there as we kind of get into what we're looking at, what talking about. So if we are observing a millimeter to the micrometer scale, so we do need special types of microscopes in order to be able to magnify that and see those small magnifications, and that is kind of what we're talking about here. So at higher magnification examples, we're talking about scanning electron microscopes. So in these shoot beams of electrons at the object instead of a light beam. So it increases the magnification into the nanoscale. This is used in academic and corporate research laboratories to help analyze fracture of surfaces. So, and I know that the University of Illinois has scanning electron microscopes. So does Eastern Illinois University in their industrial technology wing there as well. So I'm not sure how often it gets used, but they do have those tools over in those locations. So when we are talking about atomic elements, our universe is made up of these elements. The atom, of course, is the smallest unit of element, and it has specific properties that go along with that element. Now, we can break an atom down into protons, neutrons, and electrons. Hopefully you are all remembering from high school chemistry that you have protons and neutrons in the interior of it, and you have electrons that are going around the outside of your atom. So we have the nucleus, or the center of the atom, that contains your positive protons and any neutral neutrons. That nucleus is, of course, surrounded by a cloud of orbiting negatively charged electrons. We'll talk more about the electron cloud here a little bit later. The outermost electrons influence the behavior of these metals. So, i.e., typically your outermost electron shell wants to be filled, and if that is filled, we refer to that as a more stable element there as well. So, and here it gives you an example of iron and hydrogen, magnesium as some of the nucleus and your neutrons and protons as you go through. As a safety note, hexavalent chromium. So if you think about often times, especially if we're chrome plating parts for automotive industry or doing other stuff, hexavalent chromium is highly hazardous to us. So it's used with many steels and many steel types. So if you're welding and plating, they can cause chemical reaction resulting in hexavalent chromium. And you do want to be aware of the toxic fumes that this could present, so you want to make sure that you're protecting yourself. Now, there are a lot of dangers associated with that. So we are currently going to talk here about the periodic table of the elements and being able to read that chart. So it does contain 92 naturally occurring elements. So the very first one, of course, is the hydrogen atom. So, or your hydrogen, your element. So when we talk about that with the atomic symbol, so H for hydrogen, we have an atomic symbol for iron of Fe. So each element, of course, also has atomic numbers that correlate with the number of protons in the nucleus. And as we are looking at the chart, it is kind of laid out. So we have hydrogen with 1 proton in its nucleus. So, and then we go to helium with 2 protons in its nucleus, and it kind of moves on up, and we kind of read this 3, 4, 5. So as we go up with each of these, so it's a nice convenient way for this chart to be laid out. Now notice, so we have the chemical symbol, which is the H, your chemical name, it has an atomic number, and it has an atomic weight. So we also want to pay attention to the way these are grouped. So as we look down, 1, 2, 3, these rows, so to say, here are referred to as periods, and the columns are referred to as groups. So, and you can see our groups are associated here. The alkali metals are, for the most part, here in group 1. The alkaline earth metals are group 2. We have all the metalloids in here. Then we get into lanthanides, actinides, halogens, noble gases. So are the very end here, and we have other numbers that are kind of put in there as well. So pay attention to the chart. If you know how to read the chart, it can give you a lot of good information. When we're talking about compounds, compounds are when 2 or more atoms come close to one another, they combine. When that happens, we call that substance a compound. So the molecule is the smallest particle of compound that still has characteristics of that compound. So just understand the difference here between compounds and a molecule. The molecule is the smallest particle of a compound that still maintains the characteristics of that compound. Compounds have covalent bonds. So when we're talking about covalent bonds, it is the sharing of electrons. So you've got the outside orbital shell. You have atoms that have different properties and ratios of the atoms in a molecule. So we get the force developed between these 2 atoms by sharing those electrons, and that sharing of electrons is known as a covalent bond. We have ionic bonds between atoms as well. Now, ionic bonds are different. They don't share, they more or less give off their electrons in that forming process. So ionic bonds, give off their electrons as opposed to share the electrons. All of these, of course, are getting into metallic bonding that goes on. So metals don't form fixed bonding ratios between the atoms. So your electrons can move between the atomic nuclei associated equally with all of your nuclei. And voltage applied to metal creates an electric current. So you are all familiar with that. So we measure that current directly with an ammeter. So here are some of the properties that depend on bonding. So if we're looking at compounds from different properties of each element alone, aluminum conducts electricity, but aluminum oxide does not. So as we take a look at these charts, so we do get certain metals that are more conductive and certain things that are less conductive as we go. So nonmetals and compounds with nonmetals have certain properties in common. Those properties include brittle fracture and, of course, poor electrical conductivity. So the four defining properties of metals are electrical conductivity, which is the ability to conduct electricity, thermal conductivity, the ability to conduct heat, formability, which is the ability to form and change shape without breaking, and reflectivity, or shininess, or the ability to reflect light. So we talk about the body-centered cubic form. So room temperature iron has a body-centered cubic unit cell, BCC. It's a cube shaped with one atom at each corner and one atom at exactly the center of the cube. So metals can be hit and will dent rather than break. So that dent occurs as atoms slide past one another. So sliding occurs most easily in certain directions in unit cells. And it is this arrangement of these atoms in this body-centered cubic or the other cubic arrangements that help us to achieve different property structures in the material. So they form crystal structures. The metal atoms are collected together in a stable position and line up in regular orderly arrangement. So we can call this a space lattice. And the unit cell is the smallest volume that encloses a complete atomic structure. So there are three common unit cells found in these metals. So we have a unit cell for room temperature aluminum. So is what we call a face-centered cubic. So it's got your cube shape. It's got one atom in each corner and one atom at the center of each face. So the face-centered cubic structure has more directions for atoms to slide past one another than the BCC structure. Now remember, let's kind of go back for a second. Your BCC structure is your body-centered cubic. So we got body-centered cubic and face-centered cubic as we take a look at these. Then we also have a hexagonal close packed structure. So solid magnesium has this HCP structure. So those unit cells consist of three layers of hexagonal planes of atoms. Metals with these type of structures are less formable than those with BCC or FCC. And remember, this is body-centered cubic or face-centered cubic structures. And at that point, I will stop right here with this first part of this lecture, and we'll come back to finish this off in the next video.